Hi, my name is Catherine Amstutz, and this is my Physics 2211 Lab 5, Collision with a Wall. The purpose of this lab is to analyze the collision of an object on the x-axis moving at a constant velocity with a wall, and to create a computational model in GlowScript based off of Newton's second law and what we know about collisions, and then to compare the data from said computational model with the observed motion. And here is a summary of the results compared. In collisions, there's a conservation of motion. Essentially, there's no net force acting on the system. So there's no change in momentum. The initial momentum is equal to the final momentum. Momentum is mass multiplied by velocity. Because the velocity of the wall is 0, you can essentially take it out of the equation. So essentially, in this collision, the momentum of the ball that's initial should be equal to the final momentum of the ball, meaning that the initial and final velocity should be equivalent. Newton's first law, which is that an object in motion will remain in motion at constant velocity, an object at rest will remain at rest unless acted upon by a force, will apply here anytime the ball is not actively colliding with the wall. And Newton's second law of motion, which is that an object's acceleration is proportional to the net force acting on it, will be used to determine the position and velocity based on the position and velocity update formulas. The experimental model used Tracker. Essentially, I took a video of a bouncy ball colliding with a wall, including a meter stick for reference, and then created a coordinate axis and oriented it so the object can move along it in the negative x direction. I then tracked the object's position over time. The computational model was created in GlowScript and used iteration to predict the motion of the bouncy ball in small repeated steps. The system for this experiment is the wall and the bouncy ball, while the surroundings are the floor. The initial conditions are the mass of the bouncy ball, which is 0.1446 kilograms, the initial position and velocity of the bouncy ball, which were both determined using the observed data from Tracker, and delta t, which was the frame rate chosen by Tracker. Here's a video of the experiment itself. Computational model starts out with coding for the shapes that will be used in the model, such as the ball, its trail, and the wall it's colliding with, as well as the graph. The initial conditions are what I showed on the previous slide, with the exception of the fact that I did not include y values as I'm only tracking x position. The wall mass was just given one that is large enough that it will make sense during the model. Its velocity is 0. Delta t again comes from Tracker. The calculation loop starts by saying while the ball position is not equal to this x position. Now this was the x position that was the final x position observed in Tracker, essentially when the velocity is equal to 0. Then the position and update formulas derived from Newton's second law are used to update the position and velocity for both the ball and for the wall, although the wall is not going to really update. This was used to plot x and y values on the curve and in the model. And then this was used to change the velocity of the ball from negative to positive, essentially changing it from going this way to this way once it hit the wall. And then that's it. The graphs resulting from this experiment are pretty similar to what would be expected. We have a velocity that remains constant in absolute value. So the speed remains constant, it just is going in the negative x direction and the positive x direction. And then we have a position that goes to the wall and then away from the wall. As you'll notice with this curve that overlays the two data sets of x position versus time, the experimental data had a much more gradual curve than the computational model. And the computational model has a constant velocity. The derivative of this x position is constant, while the experimental model's velocity decreases over time. Additionally, the computational model takes less time to reach the same x position. So what caused this difference? The main cause was friction, which was not taken into account by the computational model. Additionally, there was a significant twist on the ball. It changed x position in addition to y position in the experimental model. And that meant that some of the initial kinetic energy and momentum went towards changing the y position of the ball, something that was not all addressed in the computational model. What would change if this were a ball made of clay or silly putty that stuck to the wall after the initial collision? Well, that would be a maximally inelastic collision, where the two objects stick together. This collision would still follow the initial momentum is equal to the final momentum. However, in this case, the wall is anchored and so much more massive than the ball that would hit it that there would be no acceleration of the wall, and it would just stick together, as you can imagine. Conclusion: I analyzed the x position and velocity of the bouncy ball as it collided with a wall. Then I created a computational model in Glow Script based on Newton's second law and compared the data from those two models.